Understanding a software system just by looking at its source code can be very time-consuming. And communicating ideas about software design or business processes is even more challenging if there is no commonly accepted way to do it. The Unified Modeling Language, in short UML, was introduced to solve this problem. UML is not a textual programming language, but rather a graphical notation consisting of diagrams that let us model software systems. We can use these diagrams to describe the objects that form a system and their interactions. UML has many diagram types. We'll be discussing the most common one. The use case diagram describes the functional model of a system. That is, the functionality of a system from the user's point of view. To describe the structure of a system, UML provides structural diagrams. We'll talk about the class diagram, which can be used to describe the structure of a system in terms of objects, attributes, operations, and relations. UML lets us model dynamic behavior too. The behavioral diagram describes the system's functionality, focusing on what happens and the interactions between objects. We'll talk about the actual diagram shortly. The best part about UML is that it's independent of any particular programming language. We can start building an object-oriented software based on UML diagrams. If those diagrams are detailed enough, they can be converted to source code. Now, let's see some real-life examples using UML. Software developers often find themselves in situations where the solution to a specific problem is not trivial, or there are several different ways to tackle the problem. It may be tempting to open up your IDE and just start coding. The next thing you know, hours have disappeared, and you are desperately searching Stack Overflow for the answer. However, it's hard to find a solution if we couldn't first formulate the question. We need to figure out what to implement before writing a single line of code. That's when UML comes in handy. Whenever something is unclear, we can quickly sketch a few diagrams to represent a specific part of a software or new functionality. The benefits of this approach are twofold. First, by thinking about classes, objects, and interactions, we gain a deeper understanding of what should be implemented without being distracted by crashing IDEs or strange compiler error messages. Secondly, the design helps us communicate our ideas with other developers effectively. We can use UML diagrams as a starting point for discussions and improvements, without having to delve into source code. Although checking the actual code is useful in many situations, it will often distract us from answering the real questions and turn the design discussion into a code inspection. Another frequent use of UML is drawing diagrams from existing code. This technique is called reverse engineering, and it helps uncover the dirty little secrets of undocumented software systems. We can use UML to create a detailed blueprint of a system. Detailed UML blueprints are usually required for software developed using the waterfall approach, and less frequently for agile projects. Although UML is excellent at modeling object-oriented systems, the fact that its platform and programming language independent make it a versatile modeling tool that's not limited to software projects. UML has been used in multidisciplinary areas, including scientific research, transportation, banking, and defense.
Okay, that's the first one. Okay, this one is a little bit longer, it's about 9 minutes. It's going to go through all of the diagrams. What I'm suggesting is that maybe you see any diagram that you want me to go through next week, and if we've got enough time, I'll go through it.
Hello coders, and welcome to the UML course for beginners. We'll look into the most widely used diagrams, their basic notation and applications. Each diagram that we will study in this course will be supported with a practical example of a system or a situation that can be modeled with its help. I'd like to start this course with a little introduction to UML and a brief overview of each diagram. How does it look like and what is it actually used for? First of all, UML stands for Unified Modeling Language, which, according to the legend, was developed when some serious IT people were fed up with an ambiguous variety of circles, dashes, stars, and clouds. UML 2.0 that we're going to study in this course consists of an integrated set of diagrams of various grid shapes and forms designed to help system and software developers to define, design, visualize, and document software system artifacts, and in some cases, some business models. UML is a set of best engineering practices that has proven to be effective in modeling large and complex systems and is a very important part of object-oriented software development. UML mainly uses graphical notation to express the software project design. UML helps teams to communicate, explore potential designs, and validate software architectural designs. The purpose of UML is to provide a standardized notation that can be used by all object-oriented methods, as well as selecting and integrating best elements of the precursor notations. UML has been designed for a wide range of applications, hence it provides constructs for a wide variety of systems and activities. For example, distributed systems, analysis, system design, and deployment. UML diagrams can be divided into two main types: structure diagrams and behavior diagrams. There are 7 types of structure diagrams: composite structure diagram, deployment diagram, package diagram, profile diagram, class diagram, object diagram, and component diagram. Behavior diagrams include activity diagram, use case diagram, state diagram, sequence diagram, communication diagram, interaction or view diagram, and timing diagram. Now a few words about each one of them. Class diagram is the central modeling technique that is used in almost all object-oriented methods. This diagram describes the types of objects in the system and different kinds of static relationships that exist between them. The 3 most important types of relationships in class diagrams, there are actually more than, are association, which represents relationship between instances of types. For example, a person works for a company or a company has multiple offices. Inheritance, which corresponds directly to inheritance in object-oriented design, and aggregation, which is a form of object composition in object-oriented design. Component diagrams illustrate how components are put together to form larger components or software systems. It illustrates the architecture of software components and dependencies between them. These software components can include runtime components, executable components, and source code components. Deployment diagram helps to model the physical aspect of an object-oriented software system. This is a block diagram that shows the system architecture as deployment or distribution of software artifacts. Artifacts represent specific elements in the physical world that are the result of the development process. The diagram simulates the runtime configuration in a static view and visualizes the distribution of artifacts in the application. In most cases, this involves simulating hardware configurations along with the software components that host them. Object diagram is an instance of the class diagram. It shows a detailed snapshot of the system state at a particular point in time. The difference is that the class diagram is an abstract model of classes and their relationships. However, the object diagram represents an instance at a specific moment, which is concrete in nature. The use of object diagrams is rather limited, namely to show examples of data structures. Package diagram is a structural diagram that shows packages and dependencies between them. It allows us to display different views of the system. For example, it is easy to simulate a layered application. Composite structure diagram is similar to the class diagram, and it is a kind of a component diagram used mainly in micro-level system modeling, but it depicts individual parts instead of whole classes. This is a type of static structure diagram that shows the internal structure of a class and interactions that this structure makes possible. This diagram can include internal parts, ports through which the parts can communicate with each other, or through which the class instances can communicate with various parts and with the outside world, as well as connectors between parts and ports. Composite structure diagram is a set of interrelated elements that interact at runtime to achieve a specific goal. Each element has a dedicated role in this collaboration. Profile diagram allows us to create domain and platform-specific stereotypes and define relationships between them. We can create stereotypes by drawing shapes of stereotypes and linking them to composition or generalization through a resource-oriented interface. We can also define and visualize stereotype values. Use case diagram describes the functional requirements of a system in terms of use cases. In essence, it is a model of intended functionality of the system, use cases, and its environment, actors. Use cases allow us to link what we need from the system with how the system meets those needs. Activity diagrams are graphical representations of workflows of stepwise activities and actions with the support of choice, iteration, and concurrency. They describe the control flow of the target system, such as exploring complex business rules and operations, as well as describing the use cases and business processes. In UML, activity diagrams are meant for modeling both computational and organizational processes. State machine diagram is a type of diagram used in UML to describe system behavior, which is based on David Harrell's concept of state diagrams. State machine diagrams depict permitted states and transitions, as well as events that affect those transitions. This diagram helps to visualize the entire life cycle of objects and thus helps to better understand state-based systems. Sequence diagram models the interaction of objects based on a time sequence. It shows how objects interact with each other in a particular use case. Similar to a sequence diagram, the communication diagram is also used to model the dynamic behavior of a use case. When compared to a sequence diagram, communication diagram focuses more on showing object collaborations rather than the time sequence. In fact, communication diagrams and sequence diagrams are semantically equivalent, and one can be generated from another. Interaction overview diagram focuses on the overview of the flow of control of interactions. This is a variant of activity diagram where the nodes depicted are the interactions or interaction occurrences. Interaction overview diagram describes interactions in which messages and lifelines are hidden. We can link up the real diagrams and achieve a high degree of navigation between diagrams within an interaction overview diagram. Timing diagram shows the behavior of the object or objects at a given time period. In fact, this is a special form of a sequence diagram, and the differences between them are that the axes are swapped so that the time increases from left to right, and the lifelines are displayed in separate compartments arranged vertically. So why are there so many diagrams? The reason for this is that this can help to examine the system at different angles, and there can be many participants involved in software development. For example, analysts, architects, coders, testers, quality control, customers, technical authors. These people are all interested in different aspects of the system, and each requires a different level of detail. For example, a coder would want to understand the design of the system to be able later to convert this design into some low-level code. In contrast, a technical writer is interested in the behavior of the system as a whole and would want to understand the product's features. UML tries to be a language that all those participants can benefit from, and possibly use at least one of its diagrams. Please give this video a thumbs up, turn the bell, and subscribe. That was me, and goodbye.
Okay, so for the prior knowledge, actually I'm guessing, I don't really know for sure what prior knowledge you have in UML, but I've identified with other students the concepts that are the most important. So number one is graph theory. Have any of you taken graph theory? You should have, but unfortunately looks like what you should have and what you have are two different things. And secondly, I've developed a pedagogy for UML that hopefully will help you out. So those are the two things that I'm going to talk about now as prior knowledge, even though in fact it's probably not. Okay, so first off is graph theory. Graph theory is real simple. It's not about pie graphs, it's not about bar charts, it's about vertex and edge, or node and edge. That's what it's about. It's only about those two things. So you can see that the top left-hand set is pretty well what a graph starts out with. Now you have either a directed graph, which would have an arrow on the edge, or you would have an undirected graph, which doesn't have any indication of direction. Now, all of these are just different types of graphs because of their orientation. I think this is pretty obvious. I'm not so sure about this being so obvious. This is nothing. This is just Rojack. This is not. This is actually an important configuration. And you'll find that if you were to spread this out, this actually looks like a tree. So it's actually one of the more important configurations. Now, the tree itself is probably the most important graph of all. Why is that?
Because there are no loops. There are no loops in that.
Well, that's true, there's no loops, but I was hoping for a different answer, but thanks, Ernest. Okay, basically, it's a hierarchy. And there are two things that we have that we use all the time in software diagrams. It's hierarchies. So just think about it, then I'll reveal them as we go. So the hierarchy is the most important, and the idea of a rooted hierarchy is almost always the most important idea with trees. Of course, you could have a tree that doesn't have a root, like this one, but it doesn't serve the same function that we need in software management. So this is the one we want. Root, and then the bottom is the leaf. Okay, so hierarchies are basically a way of ordering us traveling through the series of nodes. So what you want to be able to do is you want to be able to identify, number one, the direction. Now, in this case, most of the trees have one direction. Even though you might be able to read it in both directions, up and down, usually is the way a tree is oriented. But the way that the flow of control is, or is meant to be in that hierarchy, is usually one way. So it could either be from the leaf to the root, or from the root to the leaf. Usually not both ways. There are two main types of hierarchy. If you haven't guessed it yet, I'll use the scientific name. This one's obvious. What's this one? How do you know it? It's a very simple name how you know it. What's the way you know it?
Inheritance.
Yes, inheritance. But the scientific name is subsumption. Okay. So these are the two basic trees then. There is a third kind of tree here, which is a compositional where it's nested. So this is an unnested compositional. this is a nested. Now, in the state machine diagram, all of the compositions are nested. It's a very difficult diagram to read because of that nesting after nesting after nesting. Also, if you've got any recursive functions, they are nested, right? Recursive functions are nested, right? You understand that, right? Okay, good. So, as far as the inheritance goes, these type of diagrams can be quite easy to read, but hard to understand why they're inheritances. Of course, this particular family tree with respect to primates and all of the humanoid and the ape, the great apes, so it's partially filled with Latin, which is difficult to understand. Okay, so that ends the idea of graph theory. It's really simple. It's all about nodes and edges. And all you have to do is just configure them. You can have multiple edges from one node. You can have actually no outgoing edges from a node, like a leaf. A leaf will not have any outgoing edges. And then you can also configure them into various other shapes. But the shape we use the most is hierarchy. And that's because we do compositions and inheritance. Okay, now, how do you learn this? When I was teaching about 15 years ago, I had this epiphany that I'm sure it must be easier to teach UML than what I'm doing. And of course, the way I was doing it is the way probably you guys were taught, which is someone will say, this is a class, then you must join it here, and then you gotta memorize whether it has a name or not, and you have to memorize what type of information you have inside the class, etc., etc. So it comes across as just one whole memory exercise. But then I thought, you know, it's written, right? I mean, when you think about it, it's written on a piece of paper or a screen on your computer. And how do we learn written language that we also speak? How do we learn about our natural languages? And I tried to put the two of them together, and it seemed to actually work for my students. So I'm going to reveal to you now the process of learning UML in a slightly different way, and that way is to think of it as a written language. Now the first thing you have on your written language is the idea of the writing itself. So you can see here, for any language at all, they have things that are small little semantic-less glyphs. And I'll show you just a couple of examples shortly. So these can be called tokens. All they are is just an idea if they're a placeholder that would go with another placeholder. The next thing you've got is the idea of units. Units are generally what we have to learn in school. And of course, if we're talking about Mandarin, you'd be talking about the actual, what's it called? It's a little diagram called the thing that's got a symbol to it. A little thing about that big, with all sorts of lines and stuff. Anyway. That's it.
Like the individual characters, right?
For English, it's words.
Yeah.
Okay? So I don't know what it's called in Mandarin. And then finally, we've got writing the words in sentences. Now, there's a couple of things. You can't split a token or a letter up. You cannot split it. It is atomic. The units are atomic, but only in terms of their letters. If you split off a letter from a word, then what you have is an unreadable word. And a word that doesn't make any sense. The words are captured in a lexicon. All languages have a lexicon, which is essentially a library, either a dictionary type of library or an online type of library, but it's a library of all of the words. And as you know, our dictionaries now are very thick, hundreds, maybe thousands of pages because of the amount of words we have in our language. So what we want to do now is look at using these three things: the token, which is atomic, the unit, which is a word, which is fixed. You can't split it up, but of course it is made up of tokens. And then finally, putting words together in a sentence. So, I tried to do this in Mandarin first, and then I got some, and I hope this is right. Have I got it right?
Not bad. I have no idea what to think.
And I didn't bother translating this. I didn't bother translating this, so.
Yeah, I think so. It's the funny one. You think all Chinese will say what? Beep. Huh?
Okay, so can you start to already feel how this could maybe work for UML? All we have to do is really understand which parts of UML can be seen as a letter, which parts of UML can be seen as a word, and which parts of UML can be seen as a sentence. Okay, so this was just translated to English, which I've already done for us. Now, beyond sentences, there are further classifications of writing. So I could have gone on forever, but I decided to have paragraphs and the idea of an essay/book. Okay, so here we are. What we have to do now is we have to understand, in terms of UML, what is a letter? In terms of UML, what is a word? In terms of UML, what is a sentence, paragraph, and an essay or a book? Once you learn that, then you can put all of your 13 diagrams together yourselves. You really don't need me. Okay, so that's the prior knowledge, even though it's not prior, but I think it should be actually. Okay, so let's now go on to the actual UML. What's it all about? Okay, so UML. Everybody says it's a graphical language, but I don't like that term because it's more than just a graphical language. It's actually a framework. And it is not just diagrams. It's also got a whole bunch of other things as well. So as I go through all of that, I think you'll see that it's better to call it a 2D framework as opposed to a graphical language. But the big thing as far as where it comes from prominent object-oriented modeling methods. Those methods existed at the time, in 1996, when this was born. The people that had these languages all were congregated into one company, Rational Software. And they decided to collaborate by sharing with each other what their object-oriented modeling method was like. And so with a little bit of prompting, they managed to bring it all together and and make UML. So it comes from 3 people. So that's why it's unified. It's unified because Grady Bush, James Rumbach, and Ivor Jacobson came together and they did their things. Now, does anybody know Ivor Jacobson? You might have heard him because you do his diagram all the time. He's the guy that created the use case. You do it all the time. Anyway, so, and then secondly, as far as the modeling aspect of unified modeling language, there are 2 parts to it. Number 1, you saw in the video, there are 2 categories, structure and behavior diagrams. And secondly, which wasn't discussed in the video, you actually have built into the specification a stepwise learning, because the concepts, some are simple, but some are really complicated, really hard to understand. So certain diagrams are classified as a higher level of knowledge or familiarity than lower ones. For instance, the state machine is considered the highest level of diagram in UML for trying to learn it. Very, very hard. Whereas the use case is considered one of the beginner diagrams. And then finally, as a language, it's meant to communicate, design, and document. Now, what does this mean, design? When we say to design, we mean that you can use this as a technique to work with someone to come up with a plan of how you're going to do something. So you actually develop your plan using UML. So UML is not just for telling someone else what you have already thought. You can use it to develop the plan before you teach someone else what you've already thought. Okay, so that's very important. You can use it to design. And I've used it all the time with respect to that. Whenever I'm talking with my colleagues and we're doing some work, we just whip out the old pens and then we start to draw out a quick UML class diagram and get it figured out pretty quick. Okay? So that's important to design. Now, who takes care of UML? It is Object Management Group, OMG, not oh my God. That's a rather unfortunate acronym, actually. But, okay, so they are a worldwide organization. They were originally started to come up with object persistent models for distributed systems, and they acquired or they adopted, I don't know which way it went actually, but they became the purveyors of everything UML in 1997, and they've been doing the job ever since. So it's not unlike the consortiums that handle the management of the internet. They're a global institution. They've got people from all different countries that are employed there. Their job is to make sure that the standard is well promulgated, that is, it reaches to as many people as possible. And plus, they make sure that if there are changes to be made in it, they will do it, they will verify those changes are correct, and then they will try and make sure that it is announced and everything like that. Now, if you go to omg.org, I believe that's it, you will find these guys, and there's a button, I think it's the second one in the middle row, that is where you get the UML spec. So you can actually download it, it's free. I think that's a great, and we'll go through that next week actually. Okay, so that's UML and OMG. Okay, these are the founding guys. I think they are all still alive. This was taken many years ago. And this guy looks drunk actually. Poor guy. Not a very good photo. I should have tried to get something else, but it was such a nice photo. Okay. Now, structure and behavior. These have specific meanings for us in the physical world, right? structure and behavior. This is a structure, behavior is running out of the class or whatever like that. We know this in the physical world, but do you understand what it is in the virtual world? So you have to here unlearn and relearn. Now, number one, structure has nothing to do with physicality, but it's got everything about size. In a structure in a virtual world, you can tell where it begins and you can tell where it ends. So it means that, for instance, when something is displaying on your screen, there is no spillover. It ends there. It probably starts in one corner and then is promulgated out as a series of renderings on the pixels, but the point is there's no end that you can't see. You can see the end. It's real clear. Now the other thing is that with respect to composition, that is how you determine structure, not by what it looks like, but by what it contains. And it doesn't contain things in the normal way. As I tried to tell the 1009 people, actually composition is really a case of whether the two objects are created at the same time. That's composition. Okay? So when you're looking at structure, you have to change your mind and just look at it in terms of these things. Now, this is very important. The units, remember the units, the words? Those units cannot be repeated. That is really important. If you have a unit that's repeated, then your model is definitely wrong. There's something amiss with the way you put it together. Secondly, if any part is absent, then your whole composition fails. Okay, so that's structure. Behavior is a sequence. Now, unfortunately, we often really can't write the whole sequence because the sequence could last for years. So how do you write it? In a sequence diagram, actually you're never really writing the whole sequence. You're only writing a portion of it, a segment of that sequence. That's all you can do. So a lot of times in behaviors, we really can't model where it starts and if it is going to end, because it may not end. Now, the other thing though is that you can repeat the units. It's possible to repeat units in a behavior diagram. Only in a behavior diagram, not in a structure diagram. And there's no such thing as compositional integrity because you don't even know the beginning or end, so how can you say your composition is integral or it's complete? You just can't. Okay, so structure is about size, about composition, about non-repetition, whereas behavior is about repetition, but you don't know the size. And it's a sequence, obviously. Any questions on that? Because that's sort of a bit foreign for everybody, but you do have to relearn this if you're going to talk about UML and understand. So please don't ask me, can you repeat this class in a diagram? Obviously you can't, right? Some people try to repeat it and so it just doesn't work out. Okay, now I use version 2. I used to have the other versions, version 1.1, version 1.4, and then I kind of stuck with version 2. We're now at version 2.2. I don't really see the necessity of going to the other versions, so what I'm teaching you is slightly old. Now, it contains 4 volumes. So when you say UML, it doesn't really point to anything. It's 4 volumes. Which part of UML are you referring to? So there are superstructure, infrastructure, constraint language, and then a interchange, a diagrammatic interchange volume. So basically, the one you want to know is the superstructure. Does anybody know that superstructure has a definite meaning, not really in terms of UML, but in terms of things we build. I don't know if this is a common thing or not. On boats, the part above the water is called the superstructure. So if you think of UML, think of a boat, and then say everything I can see in UML will be the superstructure. If that's the way I think about it, it helps me a little bit in remembering that. Infrastructure is like, your backbone in your school, where all of the computers are and all of the servers are, and everything is hidden from you. And so the definitions of all the data is in the infrastructure, and the definitions of all of the employment and all of the finances, everything is buried in the infrastructure. That's the same with UML. The infrastructure actually is a set of language definitions and specifications that allow UML to be understood in other languages. So you need this infrastructure to kind of make that point. The constraint language is a Boolean language. So it gives all of the models, the elements or the words, it gives them a definition that is fairly rigorous. So a Boolean language is quite a good thing to learn. Constraint language is reasonably a good, it's like BNP. It's like BNP. Okay, so I guess you don't know what that is, right? Do a search on BNP, please. Not now, but afterwards. Okay, so that's the constraint language. And then for the diagram interchange, this is how you can get the model that you're creating to be read by Eclipse, and then for code to be generated from it. So this volume allows that to happen. It gives you all the specifications on how to address this in your design. So the superstructure, it contains 4 parts. I'll go through these with you next week. Just open it up and show you. But if you can download it and look at it, it's very unreadable, I know, but just get a feel for it from the table of contents. So there's structure part, then there's behavior part. Those are the 2 main parts that have all of the model stuff. Then you've got this supplement, which adds a whole bunch of extra annotations. Remember what annotations are? Yes. So all of them have semantic value, and they can be added to your particular model. And then finally, there's these annexes. Some of them are useful, some of them are not really useful. Okay, so actually it's a pretty simple thing. Just download the superstructure and then start looking at it. There are now 14 diagrams, not 13. The latest diagram is the profile diagram, which after looking at it, I thought it really wasn't worth it, but anyway. There are 3 behavior formalisms. There's no such thing as a structural formalism. Structure is about composition, so you have to look at what composition is defined as. But for behavior, they use 3 formalisms. A formalism is like a methodology in behavior. So, do these terms mean anything to you guys? Automata and PetriNet? No? No! What are they teaching you? Anyway, okay, so I would strongly recommend that if you just get a chance, you look up BNP, you look up Automata, and you look up PetriNet. Just become more aware, because these are the founding behavior formalisms that not only UML uses, a whole bunch of other ones use it as well. And use case is a formalism, but they don't recognize it as such. Okay, we're just about done. So now I've determined for you that your letter is a shape. You all know what a shape looks like, right? No semantics, right? Remember? Icons are not going to be in there, but they could be. Element is the definition that UML gives all of their words. When two or more elements are joined, that becomes a sentence. I'll explain that for the class diagram. It's better that I use a diagram to actually show you what I mean with that. The diagram is pretty well like a paragraph. There are 13 paragraphs, in other words. And then finally, if you want to make a book, what you do is you add a whole bunch of diagrams together. So for instance, in your design specification, not requirement specification, in your design specification, you should have class diagram. You should have activity diagram. You should have a state machine diagram and a sequence diagram. You might have a component diagram. So that design specification becomes the book in which all of those diagrams are put together as one big model.
I don't think we need this for.
Say again?
I think it's more towards the design phase. Right.
No. I'm just using that as an example.
I see.
Okay, just to make sure, I was just using that as an example. For your requirement specification, you only need one UML diagram, which is the use case diagram. But you don't even need that. You can use the use case tables. You can use a context diagram. Okay, so UML has very little with respect to requirements. Okay, now this is for your information only. All I want you to do right now is just absorb how many letters there are. These are letters. They're all shapes. They do not have any semantic by themselves. This is what I had to memorize in order to know all 13 diagrams. So let's just begin. Just look at it. Don't infer anything. You're not going to do any of these. But you will use a few in the class diagram. The top ones are structure letters. Remember I said there's a structural side or a structural section of the UML superstructure. And then the bottom ones are behavior. So immediately you can see a couple of things. Structure is mostly box-like, the letters. Behavior is mostly roundish-like. There's far more behavior shapes, letters, than there is for the structure. Far more. Okay, next one. Edges. So those were nodes or vertex. Now edges. Now you'll notice that the edges are combinations. Some only are lines, but a lot of them have two parts to them. So we would call the line that comes out of the triangle, we call that the tail. And then the triangle is part with the tail, and so it obviously is the edge for inheritance. And then finally, we have things that are in the third part of UML. So we have these type of shapes. Now notice this box on the right-hand side, top right, doesn't have a keyword in it. Doesn't have the thing with the ellipses there. So it is actually different. It's meant for an object diagram, not for a class diagram. So, you would have to go over this hurdle. You would have to be at peace, Zen-like, Zen, wusha, wusha, okay? Then you are going to memorize these if you want to know UML, okay? If you are just wanting to know class diagrams, you will see next week that the class diagrams are very small amount of shapes. There's only really one vertex and a minimum of three edges. So it depends on what your aspirations are. If you want to know UML, then you do have a lot of stuff to do, but I can obviously give you this if you want to learn. Okay, so that's it. This is the way I feel about UML. I think that it's probably super important because as Carl was that foreign guy, I think he's German or Polish maybe, the guy that you saw on the video. I mean, he laid it out pretty clear. Until we had UML, it was just hard to draw it and model it. But now that we've got it, I mean, the whole industry has changed because of UML. So if you're not going to learn anything about UML, you're doing yourselves a disservice. I'm sure when you get to your companies, someone is going to have you draw some UML diagrams. And they may not like if you sort of do them badly. I don't know how much they won't like you, but they might not like you all that much. So just please try and jump on the train, and it's a skill you should have. You really should have it. And if you want to talk more about UML and how to learn it, then I can obviously. Okay, that's it.
Other.